What does a plane have in common with a carburetor? A pitot tube also on a plane, a curveball, a perfume atomizer, and your shower. It's Bernoulli's principle. Let's get to the equation. Here it is. Got scared? I bet you did. Let's go and understand each of the terms. For example, we have here a tube full of water and it's flowing. So it has a velocity. That's why we have this term of velocity. And this tube is found at a height that is relative to something, maybe the floor, maybe the bottom of the ocean, or maybe it could be the moon, or whatever you want it to be. Depending on where you are, we also have the height, and this height is going to be relative to whatever your problem is, and actually to whatever makes it easier for you to solve a problem. Alright, let's continue. We also have water, and how do we say to the equation that we have water? Well, we use its density. That's why we have this symbol right there. And we have density in both parts. And I don't know if you kind of had a flashback right now, but this 1/2 density times velocity squared, and then this density times gravity times height. If you come from physics 1, probably you remember something called potential energy and something called kinetic energy. Kinetic energy was pretty much the same in this equation, but instead of density, we had a mass there in the equation. And also potential energy used to be, instead of a density, we had mass. So this is practically the same idea. Well, it's applying that knowledge of potential and kinetic energy to fluids. That's basically what we have in Bernoulli's equation. Alright, let's continue here. We also have another P, which is not the same as this rho. They look the same, well, not the same, but very similar. This one is a rho, it's a Greek letter, it represents density. This P, it's a Latin letter, it's gonna be representing pressure. But this pressure is not gonna be any pressure because, well, the pressure here, it's actually the pressure on the wall of the tube. So for example, if you've seen one of those movies where we have the sailors inside the submarine and he's saying, "Captain, we have a problem. There's a lot of pressure from the machines. We are gonna die. It's a big problem." And you know what's gonna happen next? Well, one of those tubes burst and you're gonna get water all over the kitchen. That's gonna be a problem. So you gotta get some duct tape to fix the problem, of course. Well, the whole idea of this part of the presentation is, well, as you can see, there's going to be pressure on all of the sides of the tube. Not just pressure going in one direction, but it's going to be going on all the sides. And the pressure that we want to talk about right now in Bernoulli's equation, it's going to be the pressure on the sides, which is going to have a special name called the lateral pressure. So that P here represents lateral pressure, the pressure that's going to be going on the sides of the tube, of this pipe. And of course we have some other symbols that you already know. For example, this G, it's going to be acceleration due to gravity. And of course we have 1/2. And 1/2 is 1/2. Nothing there to talk about. And if you want to do yourself a favor in the equations later on in the problem section, well, you can change that 1/2 to 0.5, but it's just a constant, it's just a number. Alright, let's continue. Whoa, what's going on here? We have that this thing is the same as a constant. What is that all about? Let's talk about that. Okay, let's imagine we have this crazy tube where we have a transversal section here and then suddenly the tube becomes bigger. We have a greater transversal section, and then it changes into something very small, and we get the water to travel upwards. Traveling upwards, it's not very easy. Also for water, it's not easy. I'm going to talk about that in a second. Okay, so we have here pressure to be 100,000 pascals, velocity to have 5 meters per second, and a height of 0 meters. That's going to be the variables for this part of the tube. So we have this equation is going to be applied to this part of the tube, and it's going to have a value when you plug in these numbers into the equation, and it's going to give you a number. Okay, well, let's move on. Let's see what else we have. And on this section, well, we're going to have another pressure, another velocity, and a height, which in this case are exactly the same. Well, what happens here? You have a bigger area, and as we had explained a while ago in the classroom, of course, the area, when you get more area, you get less velocity than what you have over here when you have a smaller transversal area. So the more transversal area, the less velocity you get. But there's something else going on here if you haven't noticed. Okay, so the velocity changes due to the transversal area, but the pressure is also going to be changing in a different way that maybe it's not so obvious. For example, here you have 5 meters per second in this section, and then you change it to 2 meters per second. But the pressure used to be 100,000, and now it's bigger, 110,500 pascals. It's greater now. What's up with that? Well, the idea, guys, is that most of the energy, it's not gonna go in this direction. Now it's gonna go, that energy has to be used up somewhere. Well, it's gonna be changed into pressure because, as you remember, the laws of conservation of energy, energy can't be destroyed. It can only be changed, transformed. So the energy that is not being used for the speed, now it's going to be used for making lateral pressure. All right. Now, who cares about this? I mean, okay, who cares about this? Many people. You care about this. Bernoulli's equation is going to be used for many things, and I'm going to show you right now. So right here, I'm just showing you that the pressure here, it's less than what you had over here. Just for illustration purposes, this bigger arrow represents the greater pressure than what you had over here, and the velocity here, it's greater than this velocity arrow on this part. It's just graphical information. Okay, so Bernoulli's principle, you know what? I'm gonna tell you something. Bernoulli's principle, you saw it today, probably, if you showered, because when you open the shower, you open the water from the shower, what happens? I don't know if you've noticed this, but once the water starts moving, the shower curtains are going to be pulled towards the water. And maybe you're inside, maybe you're outside. If you're inside, you're gonna be seeing this thing, and it's gonna be like, whoa, what's going on? I don't know if you've ever asked yourself about this, but there's a reason to this, and it's going to be Bernoulli's equation applied here to understand it. We're not going to apply it directly. We're just going to talk about the idea of what happens when you have a greater speed. So this is the idea, guys. Before you had the water here flowing, the particles of air here were with the same velocity as the particles on the outside. So the particles here, they're not moving so much. There is a little bit of motion going in all directions because that's how gases work. the atmosphere is a gas, so it's going in all directions, not going actually in any certain direction. They have a speed, but if you sum them, if you sum the velocity of all the particles, it's pretty much zero. But over here, different story. We get water flowing in the same direction. Those particles, they're heading somewhere. They have an objective. They're going in this direction, and they're going faster than the other particles. So what happens here? It's that the velocity of the water also makes the particles around it move faster than the particles over here. So the particles going faster, that means you get less pressure. Less pressure here means that over here there's more pressure, or the same pressure that you had before, and well, there's going to be something like a vacuum. And since there's more pressure here and there's nobody else to push over here, or there's not enough pressure as you used to have, well, this thing is going to be pushed in this direction, so it's going to be moving it over here. That's why we get this shower curtain motion out of nowhere. It's not a ghost, don't worry, nothing happens. It's just Bernoulli's principle. And you know what? This is also very, maybe you don't care about your shower curtains, but guess what? I bet you do care about that plane that you are in to not fall, right? Bernoulli's principle explains why you don't fall on that plane. That's going to be the principle behind airlift. How a plane is going to be going up is explained by Bernoulli's principle. The idea, guys, I'm gonna give you the basic idea, which is this. The wing is made in such a way that the particles that go above it are gonna be moving faster than the particles below it, just like when you had the shower over here. So these particles move faster, which means that you have less pressure. And less pressure here means that these particles that are going slower will have more pressure from the atmosphere. And what happens there when you have a difference of pressures, just like over here? You see the curtains moved in this direction. Well, the plane is going to move in this direction towards the sky. It's going to lift. And that's great. Now we have flight. That's good. Where else do we see Bernoulli's principle? Well, for example, when you have a car, you want to get the opposite of this. Instead of making the car move to the sky upwards, if you do that, that's going to create an accident. That's going to be a big problem, especially when you are a race car driver. That's why your cars, your race car drivers, your race cars, especially your race cars, have these fins on the back. These sort of like wings, they call them spoilers. And this thing, it's going to be basically the same as a wing of a plane, but it's going to have a shape that is in the opposite form. So the faster air, it's going to be going on the bottom. You're going to get something faster here. Faster air means less pressure. And here the shape of the wing is in such a way that you get less airspeed. There's going to be more pressure. So when you have this shape, the same wind is going to be pushing you down. The pressure pushes you down, and that's going to be helping you stay on the ground, hopefully also safe. Okay, and talking about safety, I'm going to talk about safety right now. Also, guys, even though you're not race car drivers, you are eventually going to be on a road trip. And in one of those road trips, probably you're going to be driving next to a big truck. Gotta be very careful, guys. Gotta be very careful, not just with your driving, but also with the driving of the other person, because if that car is going really fast, you know what's going to happen? Well, I'm going to show you right now. This is the truck. It creates air pressure. It creates air around it. I mean, air flowing through it. And then you also have an amount of air flowing next to you. What happens here when this car goes faster and this car is also going faster? You're going fast, guys. You gotta be careful though. What happens between you guys? Well, if the air here traveling between you and the truck is very fast, there's going to be less pressure. And that's why when you're going fast, but this guy's going even faster, you're going to be pulled not towards this direction, not towards the opposite. You're going to be pulled towards the truck. And I think it's pretty obvious to state that that's kind of dangerous, right? You're going to get pulled towards the truck that is very heavy, going faster than you are, and it could damage you, and you got to be very careful. Okay, but let's go to something lighter than that. Okay, also when you use an atomizer, especially one of those older atomizers, well, you're applying Bernoulli's principle, and you're applying this same idea of making air go faster and getting pressure or less pressure when you get faster air. Okay, let's imagine that we have our hands here on this pump. You push it, you push this thing. You know what happens? You get air traveling through this tube and it's gonna be exiting through here. So the air travels in this direction. It's gonna be faster than the air on the bottom. You know what's gonna happen? We get less pressure than what you have over here. And that pressure that is lower, it's gonna be, well, once you get a vacuum here, once you get a lower pressure than what you had over here, something has to fill up that void. And most likely, hopefully, it's going to be the perfume. So what happens there? The perfume or the whatever it is that we have here, could be water also, it's going to be sucked into the tube and then exiting, and it's going to be going outside. And you know the function of this, of course, but you see the principle behind this motion was Bernoulli's principle. You get low pressure here, it gets the water sucked into this section, and also the air pushes it in this direction. But the air, the low pressure here, created by the particles that are going in this direction, are going to be what's gonna make it suck and go upwards, and that's pretty amazing. Okay, let's continue over here. Let's go back to this case. So we have this, let's go back to this example that you may have forgotten about, but let's continue with it. Okay, so the idea that we had in the previous slides was that we had the greater the velocity, the smaller the pressure. Okay, and the smaller the pressure, the greater the smaller the velocity, the greater the pressure, right? So here we have more velocity, we have less pressure over here. So most of the particles are going in this direction. They're not worried about the walls around them. So most of the energy is going in the direction of the velocity. Basically, that's the idea. Okay, so the greater the pressure, the smaller the velocity. Okay, don't forget that. Let's continue. And of course, this has been all on the same height. You see h equals 0, h equals 0, and also in this guy. They're all on the same height. We were just changing the pressure on each section, but the height remained the same. But what happens if you change the height? Well, let's imagine that we want to get the water over here with the same speed of 10 meters per second, but now the height is gonna be greater. Well, that's also going to affect the pressure because, as you can see here, well, when you walk up a hill, it requires you to use your energy. It requires you to uh, use a lot of energy and you're gonna get tired. Also, that happens when you have a liquid, a fluid inside a tube. So that liquid is gonna get tired. It's gonna get tired of flowing so much, especially upwards. So what happens here is that the energy is gonna be used now for the velocity. It has to compensate for the change in the height. So now the pressure is gonna lower. It's gonna be diminishing. You have here about 23,000 pascals, a lesser amount than the pressure over here. See, so what happens here? The energy got changed into kinetic energy, but you had to compensate for the change in the energy that you had to get up there, right? Anyway, let's continue over here. So the idea, guys, to understand the constant part of the equation is the following. If you plug in these values of pressure, velocity, and height into the Bernoulli's principal equation, you're going to get a value. For example, if I put 100,000 pascals right here, and density, of course, this is going to be water. Let's assume that it's water. So you put 1,000, and then the G 9.81, and then the height, of course, is going to be 0, and then 1/2 times the density again times the velocity, which is this. You're going to get a number. And just for brevity's sake, I just placed it there. I made it previously. I did the operations myself, and I got that. And then I'm going to go to the next section. We plug in these values into the equation, and guess what do we get? We get the same thing. So that's the idea behind this symbology. It means that you plug in whatever you have on the same tube, it's gonna supposed to give you a constant. Okay, so even though this has a different velocity, different pressure, when you multiply all the terms in this way and you add them up, you're gonna get the same amount of, guess what? You know what this is? It's gonna be energy. So you get the same energy. And that's pretty much the idea, guys. And when you go over here, you also get the same amount. And if you go over here, of course, you get the same when you plug in these values. So the idea, guys, is that the energy remains constant throughout the whole trajectory of this tube with water flowing. It's an application of the conservation of energy that we had talked about before. Well, let's continue to a problem. We have here a problem that may be very familiar to you. For example, when you have a second floor or you live in a high building, well, if you don't have a pressure pump, a water pump, that's going to be a problem because you know what's going to happen? Um, you're not going to get so much pressure up there. All right, that's going to be a problem. You need to get pressure, and that's why we got a pressure pump. So the problem states here that the pressure pump has 88,300 pascals. That's what we have right there. Okay, and it has a velocity of 5.9 meters per second and a height of 1.9 meters. That's going to be the height of this pump. But over here where you want to get the water flowing, it's going to be 5.5 meters. And the velocity is going to be 3.6 meters per second. The question is, what is the pressure up there in the shower that has a lot of energy, and we want to find out the amount? What do we do, guys? Okay, this is going to be the big idea that is going to be very helpful to solve problems. Well, you see, we have a constant energy on each of the sides. Remember this part? Constant energy. This energy is the same as this energy. So we're going to have a Bernoulli's equation for this part and another Bernoulli's equation for this section, and so on and so on. So what's going to be happening here? It's that I'm going to state that the value that I have here in this part, when I apply it to my equation, it's equivalent to the same constant that I get over here with these values. So I have pressure 1 and so on, and height 1 and velocity 1. That is what I have in this part. And I have pressure 2 and height 2 and velocity 2 in this other section. And they're going to be equivalent. So this is going to be the Bernoulli's equation that we're going to be solving for to get the pressure 2. Okay, so what do we do first? I'm going to take that equation and then I'm going to plug in the values of h1, velocity 1, and pressure 1, and h2, velocity 2 into this part. Basically, what I have to do is just change the equation, the formula. I'm going to put some empty spaces there with my parentheses, and inside there I'm going to plug in or substitute the values that I have from over here from my problem. Alright, so that's what I have over here. If you look closely, that's the information that I'm talking about. So instead of pressure 1, I substitute this value that I have over here. And instead of course, density is going to be 1,000. I didn't state it in the problem. Many times when something is not stated, you gotta assume the standard. For example, in a house, what do you have flowing in a pipe? Water, right? It's not gonna be lemon juice or Dead Sea water. Nope, it's gonna be regular H2O. So you gotta put your 1,000. Your 1,000 right there at the density. And of course, they didn't state that it was on the moon or Mars. Not possible yet. Someday it will, probably. But right now we are still here on Earth. And it's going to be 9.81. And also here H1 is going to be with here 1.8 right there. There you go. And then 1/2, it's 1/2 of course. 1,000 for density, and 5.9 is going to be the velocity right there that you have here. And then you proceed to the next part. Well, I'm just plugging in the values. So this part is going to be the section for the top part of the building. That's what we have here. And as you can see here, the only literal that I have is P2, and I'm gonna clear for that. So basically what you have to do in the problems of that I'm gonna give you guys, it's gonna be just substituting the equation, substituting the values into this type of equation, and then you gotta clear for your missing value. And if the problem doesn't state one of the values, for example, if they say that it's for example, a hose on the floor, a tube on the floor, they don't change height. It's relative. Everything is relative to each other, to whatever you have. And in this case, since, I mean, if it would have been the case that, let's imagine that the room here and the pump is at the same level. So we would say in that case that height equals 0, which is the same, where you can place whatever you want, because eventually it's going to be canceling out. And that's useful when you do one of the problems of the book that you're going to be doing very soon. Okay, so anyways, let's continue with this. You gotta, well, I recommend that you start with this part. Maybe you can multiply and add, and you know what to do there. You gotta do your PEMDAS, of course. You know all about that. And it's gonna give you, for example, this amount in this case, and then you gotta continue with this part of the equation, multiply all of that. I mean, you know what to do. Remember PEMDAS, right? You gotta do first the exponent, and then you multiply, and then you multiply by this. Then you have to do also these multiplications, and then you add. Okay, that's PEMDAS. You gotta know that, guys. I'm gonna continue over here. So when we finish with this part, we get this amount, and then what's going to be next? We got to clear for pressure 2, which is this thing. Okay, and that's going to give us this amount. Alrighty, so that's it. You're done. You're done with that. That's the solution to the problem. It's 62,928. And the moral of the story is that the pressure pump had 88,300 pascals, and the pressure on the top of the building is now going to be, well, less, because that energy was used up to make it go upwards, right? There you go. That's the solution to that problem. Now, I'm going to give you the clearing for, if you don't want to do all of this procedure, I'm just going to give you the clearing for pressure 2. It's very basic. It's the same thing as what you did before, but I'm going to leave it as an equation that maybe you could use directly. Maybe it's going to be more helpful for some of you guys. Maybe for some other people, they're going to be preferring to plug in the values right there. It's up to you, okay? But I'm going to give you the equations for each of the variables that could be searched for. Okay, so the situation here is that you want to look for P2, so these terms on this side, they're being added. What you have to do is make a subtraction. That's why we have here the negative and the other negative, which are these two terms on the other side. So these two terms are now negatives, okay? Because we passed them in a sense, but of course you know from algebra that they don't really pass. You're just subtracting the same value on both sides of the equation, and that's what you have right there. So you have pressure 2 equals this, but if you prefer to have it on the left side, which is what I did right here, that will be the equation that you solve for to get pressure 2. Okay, so that's the clearing for pressure 2. I'm going to do the same thing. I'm going to clear for height 2. Alright, pretty much the same idea, but with one extra step, because that H2 is next to two factors that you gotta pass as a division. So this pressure 2 and this other term, you gotta pass it to the other side, or you gotta subtract on both sides to be more technically accurate, algebraically accurate. You gotta subtract on both sides and you get this. Anyways, what's next? This gravity and this density, you do not want it there. Gotta divide both sides by those amounts. And what do you get? This long formula. And that's going to be the formula you have to use to get the height. Alrighty, what's going to be next? How do I clear for velocity 2? You may be asking yourself. Here it is. Again, the equation is right there, the Bernoulli equation. What do you do next? Well, I gotta pass these two terms, or I gotta subtract these two terms from both sides, and I get this. So these two guys were positives, now they're negatives. And you have 1/2 times the density. Gotta divide everything by 1/2 in the density. 1/2 times density. That's gonna be next. That's what you have right there. Wait a minute. There's a B2 and a 2 on the top. Okay, be careful. That 2 on the bottom is a subindex. It means that you have a velocity for a case, for the second section. And remember this one, it's velocity 1. It's for the first section. But the 2 on the top, that's not called a subindex. It's an exponent. And you know what it mathematically means, right? And we don't want b squared. We want to get b by itself. We want b2 by itself, not squared. So how do I clear the b2? That square, I don't want it there. What do? I gotta get the square root of both sides, and that's gonna be next. And that's gonna be it. That's how we get the velocity for for b2. That's how we get the velocity for this equation. All right, and that's it for this part. How about another problem? Okay. Let's say we have a dam, You know what a dam is, right? And there's going to be water behind it. And there's water, well, trying to move in this direction because there's a hole. Let's say that that hole is 10 meters below the top parts of the dam. Okay, so let's imagine that this dam is to the brink. It's totally full. And we want to know how much velocity we get from over here. How do we get this? How do we solve this problem? Well, we're going to use Bernoulli's equation, of course, and we're going to use that last equation that we cleared for. Because we want velocity, the velocity in this part. And we have all of this. We got to use this equation. And I'm going to show you two ways of doing this. I'm going to show you first the algebraic way to get a simpler equation, but I'm also going to show you how to do it in the long way using the values that we get. Okay, so many times they're not going to tell you some information, many of the bits of information that we need. For example, if you read the problem, nobody talks about pressure. But we need to know the pressure on both parts in order to use this equation because we have pressure 1 and pressure 2. What's going to be the pressure? What is it? If they don't tell you, you got to assume that it's going to be the same. And if you think about it, it is, because what's pressing on this part of the top part of the dam? The atmospheric pressure. And what's pressing over here on this section of the exit nozzle? Well, it's basically also the atmospheric pressure, right? So we can say that pressure 1 equals pressure 2, and it's going to be 101,300 pascals. But another thing, what about the height of the first section? So this is the second section, this is the first section. The first section has a height of, what is it? Well, it says that the hole is going to be 2 meters below it. That means that I can say that this is going to be 0 meters, the one on the top, the height on the top of the dam, and on the bottom is going to be -10. Or if you want to see it in another way, maybe this could be your 0 meters and the top part could be 10 meters. It's going to give you the same information. It's going to give you the same result if you want to see it in that way. Because as I had said before, it's all relative. Okay, so we got the same pressure. And if you look closely, pressure 1 is being subtracted from pressure 2. And if they're the same values, well, we know the result of that. If I have 1,000 and 101,300 and 101,300, the same values, they're going to cancel out. They're going to disappear, totally cancel out. And what else can we cancel? You know what? We can cancel height 1 because I'm going to say that my reference, my ground is going to be 0 meters. And also I want to state something else, that the hole is going to be 10 meters below. So the language here kind of pulled me towards saying that this is going to be -10. So when I think about below, I think about negatives. So that's why I chose this convention. But if you want to do it backwards, if you want to say that this is 0 and this is 10, it's the same. Okay? But because eventually one of them is going to cancel out and it's going to be great. It's going to give you the same. Okay, let's go over here then. So this part is going to be H1. I said that it's going to be 0 meters. So 0 times, doesn't matter what we have over here, 0 times whatever is going to be 0. So basically this term cancels out because this H1, you see H1 says 0. 0 times 9.81, 0. 0 times 1,000, because we are assuming that this is water, H2O. It's going to be 1,000. 1,000 times 0, doesn't matter how much density you have here. It's always going to be 0 because height 1 as I stated, was 0. Okay, this thing, I'm not gonna be canceling just yet. So, and this thing, well, it's gonna stay there, but we're gonna see what else we can do with that. Okay, so these terms, I'm gonna cancel them. Guys, I gotta teach you this because if I didn't do that, I wouldn't be doing my job. Gotta give you the whole information. Okay, so this and this cancels out, this cancels out. So what do we have left? This term and this term, which is what we have right there. And if you notice here, we have a density and a density term, and here's another one. I'm going to factorize this density. What do we get here? Oh, it's density times all of this. There it is. What's next? Okay, this density, I just factorized it. That's good because we have a density on the bottom. You know what? The densities are going to be canceling out. That's what we have right here. We have now these terms divided by 1/2. And if you remember division of fractions, when you divide a fraction by a fraction, you know what happens? It's basically this. It's basically the following. This 1/2, it's gonna turn, when you have, this is like the reciprocal of a fraction. If you remember what happened there, it's basically just flipping the fraction and you put it on the top. So there you go. And this 1/2 turned into this 2 on the numerator. And then this 2 is going to multiply each terms of this, of the terms inside the parentheses. So what do we have there? Okay, I'm just going to put it, when you multiply the 2 times the 1/2, 2 times 1/2 is going to be 1. That's why we just have this term, the b1 squared. And then when you multiply 2 times, what is it? 2 times g times h2, it's going to be 2gh2, which, that's a great advancement, isn't it? And we're going to do some more advancements. I mean, we turned this monster of an equation into just this equation with the assumptions that we made for this problem. Now, this is for this problem, guys. Depends on the problems that you have, all right? And we can do another simplification because what do we have here? It says velocity 1 squared. I haven't talked about velocity 1 actually. Velocity 1 or velocity 2. Okay, I meant to say here velocity 1. Okay, velocity 1. Velocity 1, which is the velocity on the top of the dam of this lake or whatever that is. Well, the water there, it's not moving. Since it's not moving, it's still, as you can see, the water here, it's moving. But over here, it's very still. Or maybe it is moving a little bit, but if you get the average of the speed of the molecules, it's going to be 0. So the velocity here is 0. And over here we have another a very different velocity. So this is going to be very useful, guys, because once I place it into this part of the equation, it's going to simplify everything. You see here, velocity 1, 0 now. Guess what? This is our equation, Bernoulli's equation applied to this dam problem. Okay, I didn't say dam problem. I said the problem of the dam. That's what I'm, don't change my words. It says right here, it's a dam. It's not a dam problem. It's a dam. Okay, so the equation, it's now gonna turn into this. Thanks to algebra, this is great. Okay, alrighty, and the assumptions, of course. So this is gonna be the equation we will be using to solve the problem. All we have to do is just plug in 9.81 into the g, plug in -10 into the height. We multiply all of this, get the square root, and we get 14.01 meters per second. That's it. That's the solution. But if you say, teacher, I didn't get any of that, show me the long procedure. You know what? Let's do that. Okay, I'm going to start with the same equation, and I'm going to plug in the values for the problem. So the pressure 1, I'm going to assume they didn't tell me anything about pressure 1 and pressure 2, so I'm going to place the atmospheric pressure. Okay, so I'm going to place here 101 through 100. There you go, and pressure 2 is also there. Density, gravity, and height, got them right there. Density is 1,000, gravity is 9.81. Height 1 is 0. That's where you have the top part of the lake of the dam. Okay, and you have here 1/2 times 9.81 times 0, right? Because the velocity on the top also 0. Water is very still there, so it's gonna be 0, guys, right there. Okay, and then we have pressure 2, which is what we were talking about, and over here we have density times gravity times height 2. Density is 1,000, gravity is 9.81, height 2 is -10. Right? You do all of that, you multiply, then you divide, you get the square root, and guess what you get? It's 14, the same as before. Okay, maybe here it's kind of more obvious. These guys are going to be canceling. This guy also cancels out. And then you can do the rest. Okay, but there you go, guys. Well, that's it. I hope you have a great day. If you have any questions, I'll be waiting for you in the comments. Not these comments on YouTube, but you can send me comments on the classroom. Alright, guys, you have a great day. I wish you the best. Have a great day.